All right, 6.3 is dealing with the inverse functions. And so I'm looking at the beginning of this section. This is keying on what I was telling you guys before, that the trig functions, they are functions. The domain, the input is an angle. The output is a ratio, a raw number, okay? So when we do the inverse trig functions, the input is the ratio, the fraction. The output is an angle. You may recall from our discussion of inverse functions back in the day, if you had a function like y equals x squared, there's our standard parabola. When we considered the inverse function, we had to make it one-to-one. That is, we didn't look at the whole function. We just looked at part of the function. We didn't consider this side over here. We just looked at it from here forward, because in order for us to find the inverse function, it had to be one-to-one. That is, it had to, every x goes to exactly one y, and every y goes to exactly one x. You may remember the process for finding our inverse function. We exchange the x's and the y's. In this case, we would write this as x equal y squared. Then we solve for y, taking the square root of both sides. We had y was equal to the square root of x. All right? And this red one is the inverse function of that blue one. That makes sense. The blue one is squaring, the red one is the square root. But when we consider this function, we're only considering it for part of it. The square root function looks like this. It is the inverse of this blue part of the parabola. That's half the parabola. That's the square root function there in red. So we have to consider, when we're looking at these inverse functions, only part of the original function. Okay? Back to this particular situation. We choose a domain. I'm on page, first part of 541. We choose a domain for each function that includes the number 0. Figure 2 shows the graph of the sine function limited to negative pi halves to pi halves. This is negative 90 to positive 90. Okay? What we're saying is it is the right side of the unit circle. It is the first and fourth quadrants. All right? Cosine, we limit it from 0 to 2 pi. What you see here is these two parts of the function. That's before it repeats, before it goes back over itself, and you would have two y values mapping to one x. All right? So when we consider these inverse functions, for sine, it's going to be from negative pi halves to pi halves. For cosine, it's from 0 to pi. Okay? Cosine is from 0 to pi. All right. Let's do one or two problems from this assignment. A little bit. Okay. So for the following exercises, evaluate the expressions, and we could use the unit circle as an aid here. So Nathan, number 8 says inverse sine of pi of square root of 2 over 2. What will be the output here? So again, for
output is a fraction. Right?
Correct. Yes. For our standard for sine, cosine, and tangent,
Yep.
The input is an angle.
Oh.
The output is a ratio, a fraction, a raw number. Okay. That's for the regular. So for the inverses,
Yes.
the input is a ratio and the output is an angle. Are you with me? Thus, Nathan, when I say inverse sine of square root of 2 over 2, what is it that I'm going to be getting out? Does everybody straight with that? Thank you. An angle is coming out. When we pull out your filled-in unit circle, if you got your filled-in unit circle. If you don't, look on with somebody next to you. Might have some extras in here.
I got one.
Nate, I got you. Did you? Your quiz I have graded. You were out the other day.
Yeah. Oh, was it?
When the day we went over it, you were out, I believe.
Yeah, you were.
Remember, any day y'all are out, be sure you correspond with your teachers. You can get essentially remote attendance.
That's weird. Because I'm not really out.
Yeah, maybe you were just out part of the day. I'm not sure.
Oh yeah, I did. I left early one day. I remember.
All right. Hey, focus. Okay, here we go. Filled in unit circle. So, when we do the regular function, it takes the angle and spits out the fraction. When we do the inverse, we're taking the fraction and spitting back the angle. Are y'all with me? So in this particular case, erase it. We want the inverse sine of square root of 2 over 2. Looking at your unit circle, Jaden, what is that going to be? Should we be concerned with the x or the y, Jaden? Sine is y. One time, Jaden. Cosine before sine, c before s, like x before y. So with sine, we should be concerned with the what? Good. So looking at your unit circle, find a y coordinate in that first quadrant, the square root of 2 over 2. Is everybody okay with that? In fact, square root of 2 over 2 is 45 for both sine and cosine, isn't it?
Yes, because yes.
Which is also pi fourths radians. Are y'all with me? Okay, let's look at number 11 now. It's negative square root of 2 over 2. Well, there's a couple places cosine, Kirsten, is x or y?
Cosine is x.
Good. First of all, what do we expect the output to be here, Kirsten?
An angle.
Why is it an angle?
Because the input is a ratio.
Good. The input's a ratio. We're doing the inverse function. The inverse function takes the ratio and outputs an angle. An angle's coming out. Negative square root of 2 over 2, look at the unit circle. It occurs two places. What are they?
225 degrees and 350. Never mind. Yes, 225 degrees and then, there we go, 135 degrees.
Okay. All right. Y'all with me? That's a problem. Okay? We can't have two outputs here. We're only going to use one. That's where the restricting of the domain works. How did I just went over it. We said that cosine was going to be restricted to something. Sine was going to be restricted to something. What was the restriction for? We're dealing with the inverse here. I just said it. Inverse cosine, the domain. Anybody recall?
the domain would be the angle measure.
Okay, looking back here, I want to show y'all what this is going to be an important part. This is going to come up a few times. Okay, we have a restriction. Here it is right here. All right. For sine, negative pi halves to positive pi halves. That is negative 90 to positive 90. Nathan, that's the right side of the unit circle. Because what is sine?
Opposite.
In terms of x and y on the unit circle?
Y.
Good. So look, imagine if you're on the right side of the unit circle, can you see we have some positive y values and some negative y values?
Yes.
Now look at cosine. What does cosine say there?
0.
0 to what?
5.
Which is the same as 0 to 180. Y'all with me? Everybody's looking. From 0 to 180.
Positive and negative x value.
Bingo. That's what we're looking at here. It's relegated to, we want the positives and negatives. And so that's why for the y's, we wanted the right side, quadrant 1 and 4, and for the x's, we wanted the top side, quadrants 1 and 2. Are y'all straight with what's happening there?
Please restate that.
All right, I'll see if I can show it on the Desmos. We need to look at Desmos anyway. Okay. So what this is the graph of cosine. Okay. It is periodic. It oscillates. It's a wave. In order to consider the inverse of the function, we have to look at a piece of the function that is 1 to 1. From here to there, it is 1 to 1. What I mean by 1 to 1 is it passes the vertical test, the vertical line test, and the horizontal line test. From this section of the graph, any place you draw a vertical line, it's only going to hit that joker once. Any place you draw a horizontal line, it's only going to hit that once. Why is that important? Well, we're trying to find the inverse function. We want to take the y's and map back to the x's. If we came to out here, well, this particular y value would map to 2 different x values. So we're just going to look at just this much of it. We're going to look at just that much of the function. Well, how much is it? It's from 0 to pi. That's all we're going to look at. So when we do the inverse becomes a function. Each y is going to go to only one x. Forgive me. And the reason this is happening, Kirsten, here, is because if we think about the unit circle, okay, from 0 to pi, it's the top half of the unit circle. We're dealing with x's. On this side, we would have positive x's. On that side, we'd have negative x's. So that accommodates all of those x values. This portion of the unit circle here corresponds with values that are that portion of that sine graph. Okay. All right. For here comes for sine. All right. Same deal here. We just want to find where it's 1 to 1, where it doesn't double back on itself. I won't go from 0 to pi because there it has parabola-like behavior, doesn't it? It fails the horizontal line test. It's not a 1 to 1 function.
0 to pi halves.
0 pi halves is solid, but here that we only get positive values there. We need some negative values too.
Pi halves.
That's why it's stretched to negative pi halves. Okay. In terms of the circle, that's this. This is pi halves. This is negative pi halves. Also, we could call it 3 pi over 2. Okay, but they're calling it negative pi halves to pi halves. This portion of the graph is 1 to 1 function. So we can take each y and map it to exactly 1x. Are y'all with me? Questions? All right, so how does that apply to this particular problem? We want inverse cosine. Jaden, can you erase that mess that I wrote on the... Thank you very much, Sean. I want the inverse cosine of negative square root of 2 over 2. Kirsten has identified that's two different things. It is 225 and it is 135. We can only choose one of them. What are we going to choose? Yes, why 135?
Because it's the only one that stays in that zone.
Exactly right. It's the only one that falls in the 0 to pi. 0 to pi is 0 to 180. 135 falls in the 0 to 180. And 135 is also as radians. Pi fourths, think about fourths here, okay? 1/4 is 45, 2/4 is 90, 3/4 is 135. This 135 is also 3 pi over 4. Questions? Okay. I'm gonna do one more from 6.3. I don't know. I don't know lots of things. All right, 22 and 23, I can almost guarantee you a problem on the test like this. It says, for the following exercises, find the angle theta in the given right triangle. Range your answers to the nearest hundredth. These are both situations where the angle is unknown. Rashad, looking at number 22, if I'm standing on angle theta, theta is just a generic variable for an angle. Could be x, could be smiley face, could be whatever. If I'm standing on angle theta, 7 and 10 are the what and what?
7 is the opposite and 10 is the opposite.
Jaden, agree or disagree?
I agree.
They're right. Is everybody okay with that? We're dealing with the opposite and the hypotenuse. Since we're dealing with the opposite and the hypotenuse, Emily, which function is that?
Sine.
Nathan, agree or disagree? Sine is,
Opposite over hypotenuse.
you agree with her. That is correct. We now make a statement, a sine statement that contains those three pieces of information. It looks like this. Sine of theta is equal to opposite over hypotenuse, 7 over 10. From 0 to 5, 0 meaning I have no earthly idea how you made that statement. 5, I could teach somebody else.
5.
Okay, we want to solve for theta. Algebraically, we just undo sine. Yes.
So that's the sine -1.
Good. You say inverse sine.
Inverse sine.
We now take the inverse sine of both sides. You're going to have to write this algebraically. Jaden, you might want to write it down. Inverse sine of the left side. This is what I love about this. Yeah, isn't that great? I mean, this OneNote is just the ballingest teaching aid in the history of teaching aids. There we go. Kirsten, what happened from line 1 to line 2?
You took the sine inverse on both sides?
Correct. On the left-hand side, Nathan, now what will there be?
The inverse sine cancels.
Good. Leaving what on the left-hand side?
Sine of theta.
Just the left-hand expression.
Oh, sine of theta?
Why did we take, what was the goal? What's the goal here? The variable's theta.
Yes.
What's the goal?
We're trying to find that angle.
Good. So we chose to take the inverse sine in order to undo the sine function.
Yes.
So what?
Oh, is it just theta?
Very good. Does everybody understand the left-hand expression is theta?
Oh.
Just like we would take the square root of both sides, just like we would divide on both sides, inverse sine undoes sine.
I did not forget how to do that.
It's all right.
I realized it.
Is everybody all right with that? Now, this is the thing. On this right-hand side, what is this object? Rashad, inverse sine of 7 over 10. What is that object? I'm not looking for a value for it. I'm asking back to our original, these functions, Rashad, sine, cosine, tangent. What do they do? They're a function that maps what to what? The original function, sine, cosine, tangent, maps what to what?
Sine maps 1 over all.
Okay. This is a fundamental understanding of this sine, cosine, and tangent is getting this part.
Oh, you're talking about self-itself?
No. When we do our trig function, sine, cosine, and tangent, functions are mappings. They take inputs and put to out. Give me a second. They take inputs and go to outputs. Okay. The inputs are angles. The outputs are fractions, ratios. They're the opposite over the adjacent, whatever it might be, the particular thing. That's the original function. The inverse functions, inverse sine, inverse cosine, inverse tan, takes what to what?
It takes fractions.
Is everybody straight with what I'm saying? All right? So this object here, Rashad, inverse sine of 7 over 10,
It's going to be an angle.
is everybody understand that?
Yes.
I don't care what the angle is. You just need to know that that is an angle. It's not, this is an angle. Inverse sine of 7 over 10 is some angle. You can get on your calculator and find it. At this time, ask your calculator or just Google. What is the inverse sine of 7 over 10 in degrees?
$44.4.
44.4. Yeah, that looks reasonable to me. That's real close to 45. And can you see that this 7 side and that other side would be real close to each other? Because if it were 45, they'd be exactly the same, wouldn't they?
45, 45, 90.
Yeah, 45, 45, 90. That's correct. So if this joker here is 44.4, how much is this one? Don't use your calculator. Do not use your calculator. If that's 44.4, how much is that other one?
A little bit over 45.
Good! That's even better than an answer. A little more than 45. If that one's a little less than 45, that one other is a little more. I love it. A little more than 45. It's 45.6. Thus, this side over here, Nathan, this side length over here, how does it? Correct. Does everybody see it'll be bigger than 7? Not much, but a little. It's 7 and a little bit. 7 and a little. 7.1, 7.2, 7 point something. How could we find it more precisely? Very good, Rashad. Pythagorean theorem. Give me a radical expression, Jaden, for this side over here.
That would be square root of
You're headed in the right direction.
10 squared minus 7 squared.
Oh my goodness, Becky. Good job. Is everybody okay with that? Evaluate that. Use your calculator. Evaluate that. It's 7 and a little bit. That's 100. That's 49. Square root of 51. Square root of 51. 7.0. 7.1. 7.14. All right. One more thing. How could we find that same value? How can we find that same side using sine, cosine, or tangent? I'm going to call this. Go ahead, Nathan.
A would be the sine.
Hang on.
Okay, got it.
Hang on. Go.
Sine of 45.6 is A over 10.
Sine of 45.6 is equal to A over 10.
Negative cosine.
Thumbs up, thumbs down. Agree or disagree? Sine of 45 point. If this is A, sine of 45.6 is equal to A over 10. Rashad, agree or disagree? This angle here is 45.6.
Yes, sir.
It is right. Okay. I want to now solve for A. What should I do first?
Take the inverse sine, both sides. Or whatever that's called. What?
Yes, Rashad.
Oh. It's part of
Good. When there's a fraction involved, we can eliminate the fraction by multiplying by the denominator on both sides. Multiplying by 10 on both sides yields 10 times sine of 45.6. That is A.
Oh.
That's done. That is an answer. That is the exact value. Jaden, what is this object here?
Okay. First one.
Looking at the chart, when we hit sine, it takes a what and gives us a what? Do I have my laser pointer?
Gives us angle.
That's the inverse. Look at the graphic there.
Angle gives us a fraction.
Thus, sine of 45.6,
Fraction.
yes, is everybody straight with that? This is just a fraction. In fact, it's a fraction between 0 and 1. Okay? At this time, do 10 times sine of 45.6 degrees in your calculator. It should output that same 7.14, which means this thing here is going to be 0.714. Everybody ask a calculating device of some kind, what is the sine of 45.6 degrees? Did you get 0.714 roughly? So you can use if you turn your calculator sideways, it probably has a scientific calculator, or you can simply go to Google and say search bar sine of 45.6 degrees, and it should return 0.714 approximately.
Radians got
Yeah, you don't want radians. That's a degree measure we have there, 45.6. Well, it should be in what you're wanting. In this case, it is degree. Are there any questions about this? All right. So from chapter 6, the two that we just looked at are the two more important things. Here's the other thing from the big ideal from 6.1 and 6.2 is transformations. So back to Desmos. All right, ma'am.
Are you still discussing 6.3?
Three.
Are you moving on to 6.2?
I'm going to discuss quickly 6.1 and 6.2 combined. Okay. All right, here's a parabola, y equals x squared. And y'all may remember I talked about transformations. We had this new form, y equals a open parentheses. Yeah, let's call this. Let's do this. All right. So f of x. Everybody's looking at the screen. F of x is x squared, that parabola. And now I'm going to do transformations. G of x. G of x, we're going to do a times f of x, f, and then in here I'm going to go b, open parentheses, x plus c, close, plus d. And I talked about these transformations. A is a multiplier, 1 is fine. B is a multiplier, 1 is fine. C is an adder, I need it to be 0. D is an adder, I need it to be 0. And y'all may remember I talked about inside and outside transformations. Y'all remember that?
Inside X.
Good.
Outside Y.
Very good. And we remembered inside inverse, right? One time, inside inverse. So the B and the C are inside. They're X transformations. The A and the D are outside. They're Y transformations. Y'all remember that? And so D did what to the graph? Is it an X or Y?
Y.
Good, because it's outside. So it shifts it up or down. Take a look. It happens just like you think. Positive D moves it up. Negative D moves it down. Y'all remember that? Okay. That's the adders move it. Look at C. C's inside, so it's X, but it's inverse. It's opposite of how we think. I've got a plus in here. So if I go making C positive, moved it to the left. If I go making C negative, moved it the other way. Okay? So the adders shift it up, down, left, right, depending on X and Y. Are y'all with me? The multipliers, which are A and B, stretch or compress. So A is a Y change. It's a vertical stretch or compression. As I increase A, it stretches it. As I make A smaller, it compresses it. If I make A negative, it reflects it. Are y'all with me? Okay. B does what appears to be the same thing. We just describe it differently. B, as I make B larger, we call this a horizontal compression because it's a B change. Are y'all with me? All right. Sine and cosine behave exactly the same way. Let's take a look. M of x. A's in it. Nope. I want A to be 1. I want B to be 1. I want C to be 0. I want D to be 0. Okay. All right, y'all. The red function is cosine. Starts at 0, goes down. I mean, starts at 1 and goes down. At 0, it's 1. It moves down. All right. Now I'm going to transform it. That's the purple over the top. As I change D, what do I expect to happen?
Shift.
Good. It's going to move it up and down. We call D the midline. It splits the graph in half. Right now, the midline is the x-axis. It's 0. As I go making D positive, y'all see how the whole purple graph is shifting up? Do y'all look down here? Y'all see how? Look down here. Y'all see how it's 2? Do y'all see how 2 is the line that splits it in half? We call D the midline. Okay? All right. So we know that a D change will shift the whole parabola, will shift the whole sine or cosine wave up or down. All right. What's C going to do to us? Correct. If C is positive, the graph moves left. If C is negative, the graph moves right.
D's the midline, but isn't it also called the amplitude?
They all have words, okay? A, B, C, and D have words associated with them. And it depends on the real-world context often that we're dealing with, okay? The mathematical context, A, we call the amplitude. It's the multiplier. When we're talking about music or sound, it's the volume, all right? Turning up the volume on your speaker is the equivalent of increasing A, okay? So to show what Kirsten was asking here, I'm gonna take in A, I'm gonna make A greater than 1. First of all, it's a horizontal or vertical change.
Horizontal.
Is A inside or outside?
Outside.
Thus, it is a Y change. Okay. B and C are the X changes.
I meant vertical. I just got horizontal.
It's all right. A is a vertical change. When we go making it bigger, it's going to stretch the parabola, the curves. You see that wave function stretching? If we were talking about sound, we are turning up the music. Okay? If I make this thing between 0 and 1, it compresses it. The music is being turned down. Okay? If I make it negative, it's going to flip it. It's going to invert it. Okay? If I make it 0, then it's a horizontal line because it would be the line y equals 0.
That'd be no noise.
That'd be no noise at all. It'd be stereo off. Questions?